So there are multiple instruction classes for basically instructions and instruction set architectures. One of them is operational instructions, operating instructions, which are like arithmetic and logic operations: add, remove, add, subtract, multiply, and similarly liked operations. There are, for example, data movement operations, which include, for example, moving data from memory to registers or vice versa, from I/O devices, and so on. And there are control flow operations, which are like if statement. They act like if statements, jump statements, and so on, which basically change the way you're executing. And one thing to also think about, and that makes a difference in operating systems also, is that there are two kinds of memory architectures for instruction set architectures, where you design your instruction set architecture. One of them is what is called load store architectures, and the other is memory to memory architectures. And load store architectures is basically has the notion you cannot operate on memory directly, but you operate only on registers. So, and this is ARM processors are like that, which means that your Raspberry Pis operate that way. So every time you need to do an operation, you cannot do it on memory right away, but you need to load it to a register, and then from the register you start doing the operation. Versus memory to memory memory architectures, where you basically operate you can operate on both registers and on memory locations, and that basically means that you do not need to. I mean, you need to consider things differently when you're building your memory controller for even the operating system. And there are also differences in how the interface between input output devices with input output devices. We talked about memory mapped I/O in the second lecture, where you basically map a region of memory to the I/O devices. So when you communicate with the I/O devices, you communicate basically with memory, and then I/O operations becomes load and store to these locations. In x86, for example, you have special I/O instructions for dealing with I/O devices. They're in and out instructions, and they deal with some ports on the chips. So you can actually you do not need to talk to it as a memory, but you rather use the I/O instructions. And there are trade-offs between them. One of them is more general purpose. I leave it to you to decide which one is which. And then from another point, that architecture affects you in other ways. For example, where do you place your ISA? Do you basically make it very high level? So you basically have complex instructions. So you support if statements. Some ISAs, for example, they support Fourier transforms, fast Fourier transforms. So they support these things, and then you're very close to high level languages, because a Fourier transform would then be for you equal to a function on the ISA, or closer to hardware. And that basically means that there is much more to do as a programmer to implement something like a fast Fourier transform, and there's much more for you to do as a compiler, as a systems programmer who designs compilers, when it comes to what you need to actually to reach uh, the instruction level on the machines on the chip. And these are two ways to think about them, but they also map nicely to what is called the RISC and the CISC machines. RISC machines are basically short for reduced instruction set computers, and these are computers that operate closer to the hardware, while CISC machines are complex instruction set computers, and there you have a lot of things that are implemented in hardware, or that can be implemented in hardware, or are not implemented in the hardware, but are implemented in the instruction set architecture. And then basically from the ISA to the microarchitecture, you have a mapping to the actual hardware. So if you have, for example, an FFT, if you call an FFT and it's not implemented in hardware implemented FFT, then you would basically map this down to whatever smaller less complex commands you need to do an FFT, which basically would be load, store, add, and multiply, for example.